Hey everyone, so welcome to Chapter 6. In this chapter, we're going to talk about a special type of continuous distribution known as the normal distribution. So what is section 6.1 about? It's just all about introducing what the normal distribution actually is. So recall the definition of a probability distribution. We need to somehow list all the possible outcomes a random variable can attain and their corresponding probabilities. However, when it comes to a continuous random variable, this is impossible because a continuous random variable can take on an infinite number of values, so therefore we can't list all of them out and their associated probabilities. Instead, we will draw a curve that presents all the possible outcomes the random variable can hold, and that will go on the x-axis. So the x-axis will be all the possible outcomes the random variable can have, and their corresponding probabilities will be represented by the area under the curve. So for a continuous random variable, think that the probability is equal to the area under that curve. So why do we talk about the normal distribution? So it comes up in many different applications, from pharmaceuticals to animal science and many other more. So many continuous random variables tend to have probability distributions that are bell-shaped and symmetric. We say these variables are approximately normally distributed. So in this chapter, we'll focus on drawing normal distribution curves. So here on the x-axis, you have all the possible values your random variable can take on will be here. And under the curve, we have the area, which is represented by the probability. Now, the shape of this curve will be determined by two different parameters, by the mean mu, so that will be where is the center of the distribution. For this example, the mean is right here in the middle, mu, and the standard deviation, sigma. That will determine how spread out the actual distribution is. Now that we've kind of introduced it, let's talk about some of the properties of the normal distribution that I think you should know. The first one, the curve is bell-shaped, so it just looks like a bell, and that can be illustrated down here in the graph. The second one, the mean, the median, and the mode are all located at the center, and they are equal. So you should know, if I tell you something is approximately normally distributed, I tell you the mean, I tell you the median, or I tell you the mode, and I ask for one of the other two, you should know how to find that. It's just going to be the same because they're all located at the center and they are equal. The third one, the curve is unimodal. That just means there is one mode, so one peak in the distribution. The curve is symmetric about the mean. What does that mean? That just means an equal amount of data will fall below the mean as above the mean. The curve is continuous, so that means there are no holes or gaps in the distribution. An important one, the curve never touches the x-axis. Theoretically, this makes sense because it's a continuous random variable and it can take on an infinite number of values, so we don't know what the largest or smallest value is. Therefore, it will never actually touch the x-axis or cross it. The total area under the curve, it is a probability distribution, so therefore the total area should be 1 or 100%. And the final thing, the empirical rule applies here. What in the world is the empirical rule? So we'll talk about that next. So what's the empirical rule? The empirical rule tells us the following. So if we're looking at one standard deviation from the mean, that would be the interval mu minus sigma to mu plus sigma. Then by the empirical rule, 68% of the data values will fall within this interval here. Now this is for 1 standard deviation from the mean. For 2 standard deviations from the mean, it would be mu minus 2 sigma to mu plus 2 sigma. And within this interval, we expect 95% of the data values to lie within there. And the final one that we're going to talk about is 3 standard deviations from the mean. That would be mu minus 3 sigma to mu plus 3 sigma. And within this interval, we have 99.7% of the data values fall within that. If you want to look at that pictorially, here you have the mean mu. Say we go out 1 standard deviation from the mean, that would be around right here and right here. This lower boundary is obviously going to be mu minus sigma, and this upper one is mu plus sigma. And the empirical rule says that in between these 2 boundaries right here, we will have 68% of our data values will fall within here. So the area in between here is equal to 68%. Now if we go at another standard deviation on both sides, so we're looking at mu minus 2 sigma to mu plus 2 sigma, that would be from this solid line here to this solid line here. And that total area from here all the way to this upper cutoff here is 95% by the empirical rule. And the final one, if I go out another standard deviation on both sides, this would be mu minus 3 sigma is this one right here. And mu plus 3 sigma is this one right here. And the total area in between these two is 99.7%. That's just what the empirical rule states. It gives us a rough estimate of the percentage of data values that fall within 1, 2, or 3 standard deviations from the mean. But we're not always going to have a value that is within 1, 2, or 3 standard deviations from the mean. But let's look at an example when we do. It says, using the empirical rule, solve the following problems for a normal distribution with a mean of 80 and a standard deviation of 10. Now, the mean is located in the center, so we can say the mean mu here is equal to 80, and its standard deviation is 10. So let's kind of use the same picture as we had on the last page. We go mu minus sigma and mu plus sigma. So that would be 80 minus 10 is 70. And then 80 plus 10 is 90. And within this region here, from 70 to 90, we have 68%. Then if we go at another standard deviation, that would just be subtracting another 10. So if I subtract another 10 from 70, I get 60. And if I add another 10 to 90, I get 100. And this is 2 standard deviations from the mean now. And the total area of that here is 95%. And the final one, if we go at another standard deviation on both sides, we're taking 10 off of 60, so that would be 50. And then we're adding 10 to 100, so that would be 110. And in that interval, we have 99.7% of the data values. So that's just using the idea on the previous page of going out mu minus sigma to mu plus sigma, mu minus 2 sigma to mu plus 2 sigma, and mu minus 3 sigma to mu plus 3 sigma. Now let's use these numbers here to get an idea of how to do these problems. What percentage of values fall between 60 and 100? So here we have 60 and 100. This is actually just 2 standard deviations away from the mean. So then by the empirical rule, we have that 95% of the data is within there. So 95% is the answer to the first part. The next one is a little bit more tricky. It says what percentage of values fall below 70? Then, if we look at the graph up here, we're just looking at this area shaded in green, the area to the left of 70. Now this one is a little bit more difficult. So let's use a couple of ideas. We know that 68% of the data is going to fall within this middle section right here from 70 to 90. Now, if 68% falls within this region here, that means that from 17 over this way and from 90 over this way, the total area in those two added together will give me 32%. Now, since the standard normal distribution is symmetric, we went on an equal number of standard deviations on both sides. So therefore, the area in each of these tails is going to be the same. So that means the area in this tail is 16%, and the area in this tail is 16%. Now, it says what percentage of the values will fall below 70. We have 70 right here, and we just found the area to the left of it is 16%. So that means the percentage of values that fall below 70 is indeed 16%. Another way you could have said that is you take the total area of 100% minus the middle sector right here, and that'll give you the remaining area of these two parts, and then I divide that by 2, and that will give me 16%. Now, the next one, within what boundaries will 68% of the data values lie? This is just using the first rule. So under the empirical rule, we have 68% of the data values will fall within 1 standard deviation of the mean, and within 1 standard deviation of the mean, that is from 70 to 90. Therefore, our boundaries will be 70 up to 90. Now remember that area under the normal curve represents the probability. The empirical rule can only tell us so much about calculating the area under the normal curve. For example, if we wish to find the area between other standard deviations of the mean, say between 1.5 standard deviations of the mean, we could no longer use the empirical rule because it only tells us within 1, 2, or 3 standard deviations of the mean an approximation of the percentage of data values that are in that range. Then we need to introduce something a little bit more standard, and we're going to call this a z-score. So the z-score represents the number of standard deviations that a data value falls above or below the mean. And we have 2 different formulas here. So for a sample, we have that our z-score, so we're just going to denote that as z is equal to some data value that we're interested in, x, minus the sample mean, because we have sample data, so we know the sample mean, and then divided by the corresponding sample standard deviation. And here x is some data value we're interested in, X bar is our sample mean. And S is the sample standard deviation. Then, using this idea and using population parameters, we have that Z is equal to, again, some data value X minus the population mean U divided by the population standard deviation sigma. Again, X is some data value of interest. Here, mu is the population mean. And sigma is our population standard deviation. So you may be asking, does it matter which formula I use? So theoretically, no. You're still taking some data value, you're subtracting off the mean and dividing by the standard deviation. But if you have population data, technically this sigma is going to be off. So whenever you had sigma was equal to the sum of the xi, so each data value minus the population mean, that quantity squared, divided by n, and n was the sample or the total population size, and s, we had this was equal to basically the same thing, but we didn't have the population mean, so we had to use the sample mean. So this should actually be the square root of this. That's the definition of sigma squared, so I need to take the square root. Then here I divided by n minus 1. So there's a slight difference here, but if I tell you what the standard deviation is already, that's not going to make a difference which formula you use. Now let's look at something that's kind of insightful. So if z is negative, so that means in this formula up here that we get a negative value. Recall that s is obviously the square root of the variance, and the variance is positive, so therefore s is positive and sigma is positive. So the only way that z could be negative is if x minus x bar is negative, so it's less than 0. And that implies that our data value x falls what? Below the mean. What does that mean? So if x falls below the mean, this data value x is just smaller than x bar, so when I do the subtraction here, I get a negative number. Using that same idea here, if z is positive, then this numerator is positive, so that means x is actually greater than x bar, so our data value x falls above the mean. And the final one, if z is 0, then that means x minus x bar is 0, or that x equals x bar. So our data value x actually is the mean. And hopefully that should make sense. Now moving on to an example to illustrate this. For an example, say you score 96 on your first stat test and a 71 on your first history test. If you wish to compare these scores, they first need to be standardized in order to make the comparison. So, if the mean score on the stat test was an 82 with a standard deviation of 10, and the mean score on the history test was a 62 with a standard deviation of 5, then we can calculate the z-scores for the two. Then let's set up two little columns. So we have for your stat exam here, and for your history exam here. Let's do the stat one first. So the data value you actually got is the exam score you got, which was a 96. So therefore, the little x value is 96. The stat test had a mean of 82. So we'll just say it's sample data. So x bar is 82. And it had a standard deviation of 10. So S would be 10. It doesn't matter if you would have put mu or sigma here because I already told you the standard deviation. So it doesn't matter really which one you use, but I'm just saying in this case, you're doing an exam and you're not going to give the exam to all of the students. You're just going to give them to the students in your class, and that's a sample. Next, the history. So you got a 71, so the data value there is 71. The mean was a 62. And the standard deviation was 5. Now what I want to do is find the z-scores of these two and compare them. And whichever one is higher, that means I did better on that exam compared to everyone else. Let's look at this first one, the z-score for the stat exam. Z is equal to x minus x bar over s. So why did I put them in this list? That way I can just look at these and plug them into the formula. Then that would be 96 minus 82, and then divide that by 10. And that would give me 14 divided by 10, which is 1.4. Then doing the same thing over here, I have z is equal to x minus x bar over s. X is 71, x bar is 62, and s is 5. That is 9 over 5, or 1.80. Now, since I did 1.8 standard deviations above the mean on my history exam, and I did 1.4 standard deviations above the mean on my stat exam, then since this z-score is higher than this, I did relatively better on the history exam. Than that of the stat exam. But hold up, I got a 96 on this test and I got a 71 on this test. How did I do better on this one than this one? Think of it this way. If I had this history test here was out of 75 points, or you say maybe like 72 or something like that, and this exam was out of 120 points, then these two don't have equal units of measure because they have different scales. That is why I need to standardize these test scores using this z-score to make comparisons about them. Now this next thing says, remember, z-scores represent the number of standard deviations each value is from the mean. So then just interpreting one of these, you could say your history z-score of 1.8 tells you that your exam score was 1.8 standard deviations above the mean. And why is it above the mean? because we got a positive z-score, and on the previous page, if we had a positive z-score, our data value falls above the mean. So that idea follows here. Now, when we standardize all of the values our random variable can take on, then we transform our distribution to have a mean of 0 and a standard deviation of 1. If you want to look at this pictorially, say here I have my random variable x that is normally distributed, and it has some mean mu and some standard deviation sigma. Then transforming it using that z formula, I have it is now distributed as z with a mean of 0 and a standard deviation equal to 1. And this is using the z-score formula from the previous page. And after this transformation, the normally distributed variables are converted into what we call standard normally distributed random variables. So a standard normal, z, is distributed normal with a mean of 0 and a standard deviation of 1. That's how we will write it. Now, let's talk a little bit more about standard normal distribution curves. So this is just basically the same picture from the previous page. So we have all the possible z-scores we could get. The mean in the middle is 0. The standard deviation is 1. And the area under this curve is still the probability. We still have a continuous distribution. Therefore, the area under the curve represents the probability. Notice the differences and similarities between the normal curve and the standard normal curve. So in the normal curve, the mean here was the actual mean of our sample or the population, and the sigma was just the population standard deviation or our sample standard deviation. But in this case, we standardized it, and then we get a mean of 0 and a standard deviation of 1. That's just the same idea we talked about on the previous page. Now, just as in Chapter 5, we wish to calculate certain probabilities of our random variables. But before we get to calculating probabilities of normally distributed variables, let's focus on calculating probabilities of z-scores using our standard normal distribution curves. There are 2 steps for this. So the first one would be draw the normal curve, and shade the appropriate region. Then once we have figured out the region that we actually want to find the area of, then we go to the second step. Find the probability of the shaded region using the standard normal distribution table. So dist will be distribution table, and this is on pages 7 and 8 of the distribution tables packet on Canvas. Now let's look at this for a couple of examples. Now I gave you this thing up here again, just to let you know that the standard normal distribution table can be found on pages 7 and 8 of the distribution tables packet on Canvas. Now I will pull that out real quick, and we will find some of these probabilities using the packet. So first, let's talk about what the packet will actually tell you. Let's go to page 7 real quick. Here, if you look at it, it'll have, here you have the ones place, and then you have the tenths digit, and that'll be what is on this axis here. And then the second decimal place will be up here. Say I wanted to find what's the probability of z being less than negative 3.22. Then I would go negative 3.2 and then to 0.02. And since I said what's the area to the left of that already, it would just be this here. Important thing to note that table entries for z is the area under the standard normal curve to the left of z. It'll tell us the area to the left of this z-score in the table. So if we want the area to the right, then we need to take 1 minus the area to the left. And I will show that later in an example. The first one, let's do the steps here. So first thing, we have drawn the curve. Now we want to shade the appropriate region. It says, what is the probability of getting a z-score less than 1.20? So we know that our z has a mean of 0. So we'll say 1.2 is probably around right here. And we're interested in what's the probability of z being less than that. That means we're interested in all of this area to the left. All of it. Then, using the standard normal distribution table, it'll actually tell us this because it's already the area to the left. And all I need to do is go in my standard normal distribution table to 1.20 and look at that area. 1.2 and then over to 0.00, and that is 0.8849. That tells me the area to the left of 1.20, that z-score is equal to 0.8849, and that is just what I want for this first part. So the answer is 0.8849. Now let's look at the second one. What's the probability of z being less than or equal to negative 2.24? Now let's look at the table to find this. If you want to draw it pictorially, you can do the same thing. Here you have the mean of 0, and negative 2.24 is probably right around there. And we want the probability of z being less than or equal to that, so we want the area to the left. And the table will already tell us the area to the left, so we don't need to worry about that. Then we go negative 2.24, and that is 0.0125. 0.0125. Now, one thing I will notice here, some of you may say, does it make a difference if I have just less than and less than or equal to? And the answer is, for a continuously distributed random variable, the answer is no. Think of it this way. We said that probability was represented by area, right? So here we have the z distribution. We have some curve, and we want to look at what's the probability of z being exactly one value. So say, what's the probability of z being negative 1.20, just like in this first case, but we just look at the negative one. If we're interested in what's the probability of z being exactly that value, then we want to kind of look at what's the area that it can take up. Then let's think of it this way. You can find the area of z being less than this value by taking rectangles here under the normal curve, approximating that area with rectangles, finding the area of all those rectangles and adding them up. Now, if I want to look at the probability of z being equal to that 1.20, that is just a vertical line. There is no width to that line, and remember that the probability was represented by the area, And for a rectangle, so rectangle has area, length times width. And in this case, this line has a length. It has some height up to this curve, but it has no width. Therefore, the area is 0, and therefore the probability of any one single outcome for a continuous random variable is 0 using that logic. So that means that it doesn't matter if I use less than or equal to, I will get the same thing. Now let's look at this next one. What's the probability of z being greater than 2.11? So let's draw this. We have the center has a mean of 0, and we want to look at what's the probability of z being greater than 2.11. So in this case, we want the right-hand area over here. But our standard normal distribution table will only give us the area to the left over here. So it'll give us all of this area. It'll give us all of that in the green. Then how do I find the area in the red? Well, since this is just the complement of this, I can take 1 minus the area in green right here to find the area in the red. And this area in the green here is just equal to the probability of z being less than or equal to 2.11. Then I just need to look up this probability in the table and take 1 minus it. And that would be 1 minus, if you look up the probability of z being less than or equal to 2.11 in the table, we go 2.1 and then 1 here. That's 0.9826. So that's 1 minus 0.9826, and that will give us a probability of 0.0174. So if you're given a problem where you're looking at the area to the right of something, then you want to take the area to the left and then take 1 minus that area to get the right-hand area. Using that same idea, let's look at this next example. The probability of z being greater than negative 0.94. Using that same idea we had on the previous page, this would be equal to 1 minus the area to the left. So that would be the area of z being less than or equal to negative 0.94. And if we draw this pictorially, we have the same idea. Here is the mean of 0. Here is, say, negative 0.94. And we want the probability of z being greater than that. So we're looking at this area here on the right. Now, looking up the area to the left here in the table, we have the probability of z being less than or equal to negative 0.94 is equal to, so negative 0.94 is 0.1736. So we have 1 minus 0.1736, and that will give us the final answer of 0.8264. So we've talked about whenever z is less than or equal to some value and greater than or equal to some value. So we know how to do that now. What happens if I want to look at the area between two z-scores? Let's look at this first example and we'll illustrate how to do that. Let's do it first graphically. It'll be a lot easier to interpret that way. So here in the middle we have the mean of 0. Now we want to go out here to 2.12 and then out here to negative 1.50. This isn't drawn to scale. So I apologize, but I'm just trying to make it graphically feasible. And I want the area in between these two. That means I'm looking at this area right here in the middle. Now, our standard normal table will only give us the area to the left of some value. It won't give us the area in between these two. Then, an easiest way to find this middle area, I want to look at the probability of z being less than or equal to this upper boundary here. And that'll give me all the area to the left over here. So I want the probability of z being less than 2.12. And then I want to take off the area to the left of negative 1.50. And that will take off this area here and leave me with the area I want in the middle. Then this is what we have. The probability of z being less than minus 1.50. Then if we look these two up in the table, the probability of z being less than 2.12 is equal to 0.9830. That means from here over all the way till the end has area of 0.9830. Now I want to look at this area here from negative 1.5 all the way to the end. And that area is 0.0668. Then to find the area in between these two, I just take the difference of these two. And that would give me the area in between those two z-scores is 0.9162. Now let's look at another example using this same idea. It says the probability of z being in between 0.54 and 2.33. So we'll say 0.54 is probably right here, and 2.33 is probably right there. And we want the area in between those two. Then using that same idea as we did here, we can take the probability of z being less than or equal to the upper z-score minus the probability of it being less than or equal to the lower z-score. And that will tell me this area in the middle right here. If I look up these in the table, this first one is 0.9901, and the second one is 0.7054. And if I simplify that, I get 0.2847. So that's how I would do it. If you are looking at the area of it being in between two z-scores, take the probability of it being less than the upper boundary and subtract off the area of the lower bound to the area of the left of the lower boundary, and that will give you the area in between. Now, what if we're given a certain probability and we need to find the associated z-score? How do we do that? So this is kind of like reverse what we just did. The first step would be draw the z-curve and shade the appropriate region. And the second one is find the area to the left of the unknown z-score. Then look for that probability of the area to the left in the table, the standard normal table. Now, let's look at some examples to illustrate this idea. The first one says the probability of z being less than some unknown z-score little z is equal to 0.8554. Now let's think of it this way. This is much larger than 0.5. Therefore, this must be a positive z-score. Let's say it's around here. And the area to the left of it is given by 0.8554. So this is our unknown z-score here. Since it's already given us the area to the left here, all we need to do is go look for this area in our standard normal table and look for the associated z-score. And if we do that, we go, what is it, 0.8554. Here it is, 1.06. So it's right there. Therefore, this z-score here is equal to 1.06 using the table. There is another way you can do this using the calculator, and I want to show you real quick. And to do that, you go second vars. That'll take you to the distributions. Then you go to inverse norm. You tell it the area you're looking at. In this case, we're looking at the left-hand area, and that is 0.8554. You tell it the mean. So since we have a standard normal distribution, the mean is 0 and the standard deviation is 1. And we were already given the left-hand area, so we don't change this tail. Then hit paste. And then it'll tell us the exact z-score. So in this case, it was 1.059. In this case, it just rounded that up to 1.06 because our tables only go up to 2 decimal places. Now let's look at this next one. Find the probability, or find a z-score such that the probability of z being greater than the z-score is 0.0136. And that means that our z-score must be up here if the area to the right of it is so small. So Sarah's z-score is right here. And the area to the right of it is 0.0136. Then the area to the left of it, we can take 1 minus that to find this area over here. And if we do that, we get it 0.9864. Then we need to look in the standard normal distribution table for a z-score with the probability of getting a z-score less than this little z value is equal to 0.9864. So let's do that. And if I do that, I should get, here it is, 0.9864. That is it. Z is 2.21. This implies that our unknown z-score we're looking at is 2.21. So if you're given a right-hand area, find the left-hand area first, and then use this area to find it in the table, just like we did. So let's look at another example of this. Find a z-score such that the probability of z being greater than or equal to it is equal to 0.0708. Again, since this probability is so small and we're interested in the area to the right, it must be up here somewhere. So here is our unknown z-score, and the area to the right of it is 0.0708. Then, using that same idea, we want to find the area to the left of it, so we can find that area in the table. And to find the area to the left of it, I just take 1 minus the area to the right, so that's 1 minus this, And if I do that, I get 0.9292. Then I need to find a z-score such that the probability of z being less than or equal to this unknown z-score is equal to 0.9292. So just do the same thing you did in the last one and look for that in the table. And 0.9292 is right here, 1.47. This implies that the z-score we're interested in is 1.47. So again, now we've looked at finding unknown z-scores whenever we're telling the area to the right and to the left. What happens if we're told the area in between two? Can we find the corresponding z-scores? And the answer is yes. Let's look at this one here. The probability of negative z to positive z is equal to 0.8664. Then we have some negative z-score here to some positive z-score here. And the area in between these two is 0.8664. Then, in these two tails added together, we should have 1 minus this area remaining. And that remaining area is what? Let's look at 1 minus 0.8664. And that means in these two tails here, the total area is 0.1336. Now recall from the properties of the standard normal distribution that is symmetric about the mean. So that means an equal percentage of the data will lie below this negative z-score as above this positive z-score. Then the area to the left of this negative z is just 1/2 of this area here. And 1/2 of this area here is 0.0668. And that's this area here to the left of this negative z. So now that I have the area to the left of some z-score, I can find the corresponding z-score in the table. And if I look for that, it's obviously going to be negative because the probability is less than 0.5. And if I look for this in the table, it will be 1.50. So negative 1.50 is where we have 0.0688. So this implies that z, or the negative z, is equal to negative 1.50, which implies that the positive z is equal to 1.50. Or another way you could write it is the positive and the negative z-scores you get are positive and negative 1.50. Now let's look at this last example of section 6.1, and it's using the same idea that we just did in the previous question. The probability of getting a z-score in between this negative z-score and positive z-score is 0.9182. That means I have some lower negative z-score here, and I have some positive z-score here. And the area in between these two is equal to 0.9182. Then the area in these two tails added together should be 1 minus that. And if I do 1 minus 0.9182, the area in both of those tails added together should give me 0.0818. And using the same idea, the standard normal distribution is symmetric, so it has equal area in each of these tails. So therefore, the area in this left-hand tail here is equal to 0.0409. Then now I have the area to the left of this negative z-score, So I can again go in the standard normal table and find this corresponding negative z-score. And if I do that, I get, where is it? Here it is, negative 1.74. So that means that this negative z-score here is equal to negative 1.74, which implies this positive one up here is 1.74. That means our positive and negative z-scores we were looking at in this case were positive and negative 1.74. And that is all for section 6.1 of this. We will talk about 6.2 in an upcoming video.